Yeah. Hi, good evening. Yep.
Hello, good evening, sir.
Good evening. Okay, so uh, let's wait 2 minutes, then we'll discuss. Okay, so let's start. Okay, so today I think we will discuss first two questions that Seeker sent me today. Then we will discuss more questions. Okay, so let me just share my screen. So actually regarding the first question, Sika, I actually discussed many times, right, in the session.
So actually, I
Okay.
was unable to solve it now.
Yeah. No problem. I'll discuss this again. But okay. So let me just write the first question. So question number one. For a bimolecular reaction, so for an okay, let me just for a bimolecular gas phase reaction, let's say it is P plus Q to R. So the pre-exponential factor is given here. Pre-exponential factor is 1 times 10 to the power minus 3 decimeter cube mole inverse second inverse, and we have to find out the standard entropy of activation at 25 degrees centigrade. So standard entropy of activation at 25 degrees centigrade with unit Kelvin inverse mole inverse. Okay, so here actually the standard concentration is given, which is actually 1 mole per liter. Planck constant is given, and the universal gas constant. So actually here the Planck constant Kb is given, universal gas constant, which is capital R, is given, and the Boltzmann constant Kb and the Planck constant H is given also. These three quantities are given. So here it is a bimolecular gas phase reaction where the reactants are P plus P and Q, and the product is R. So and the pre-exponential factor is given. So pre-exponential factor means the question is from the transition state theory approximation, right? So we have to find out the rate constant from using the transition state theory. Okay, so here actually I am just guiding you how to solve this question. So basically in transition state theory, let's say A plus B to first these two reactant molecules will form an activated complex AB, and then from that activated complex to product P, right? and there is an equilibrium between the activated complex AB and reactant molecules, these and these. There is an equilibrium, and that in short, the rate constant using the transition state theory approximation is K rate, which is the rate constant for this reaction, equal to KBT divided by H times K equilibrium double dagger. So this is the basic relationship. Here K equilibrium double dagger is actually the equilibrium constant between this activated complex AB double dagger and the reactant molecules. Okay, so this is actually an equilibrium constant, and we know from thermodynamics that any equilibrium constant you can write by K equilibrium equal to exponential minus Gibbs free energy delta G divided by RT, right? You know from this in thermodynamics. So you know from the thermodynamics. So here this K equilibrium double dagger is also an equilibrium constant. That means we can also write this KBT divided by H times exponential minus delta G double dagger divided by RT. This is the rate constant. Okay, now we have to find out the pre-exponential factor of this expression. To do that, so we have to first delta G means delta H double dagger, which is enthalpy of activation, minus T delta S double dagger, right, divided by RT. So it will be equal to KBT divided by H times exponential minus delta H double dagger divided by RT times exponential plus this minus and this minus will become plus, TT will cancel, and it will be delta H double dagger divided by R, right? So here we can see that there is a relationship between the rate constant and the enthalpy of activation and the entropy of activation. Now to find out the pre-exponential factor, so we have to find out first, we know that the H equal to U plus PV. We know from thermodynamics, which is the enthalpy, H is the enthalpy, U is the internal energy, and H equal to U plus PV. So basically delta H will be delta U plus P delta V, and using the ideal gas approximation, P delta V means delta N RT, right? Delta N is actually the change of molecularity. That means the number of molecules participating in the activated complex minus number of reactant molecules. Okay, change of molecularity. That means number of molecules in the activated complex minus number of reactant molecules. Okay, so we know that the delta H double dagger can be written as delta U double dagger plus delta N double dagger RT, right? Delta U double dagger is basically the internal energy of activation, which we can write as the activation energy, EA. Okay, now just put it here, put the value of delta H double dagger in this equation. There is something is missing. No, okay. So basically it will be no, delta H double decker equal to delta U double decker plus delta N double decker RT. Oh no, this is the actually, okay, so this is actually the internal energy of activation. Okay, so just put it here. So rate constant will be equal to just kBT divided by H times exponential minus delta H double dagger, that means delta U double dagger plus delta N double dagger RT divided by RT times exponential plus delta S double dagger divided by R, right? So now actually we have to find out the relationship between the activation energy EA and internal energy of activation delta U double dagger. Okay, so basically it will be just, how can we write it? Actually it will be, so from Arrhenius equation we can write it. Okay, you don't have to just remember all this equation, just I will just, okay. So from Arrhenius equation we know that rate constant equal to some pre-exponential factor times exponential minus EA by RT. So here if you just ln k by dt, then you will get EA divided by RT square. Okay, and from thermodynamics also you know d ln k by dt equal to delta U double dagger by RT square. From thermodynamics you can write it. Something is missing. Okay. d ln k by dt equal to A divided by RT square. Okay, so here it is k equilibrium, that means let me just fix it first. So k equal to kBT divided by H times k equilibrium, ln k equal to ln kBT divided by H plus ln k equilibrium. So ln k equal to 1 upon t plus ln k equilibrium. Now d ln k by dt, d ln k by dt, okay, so this is d ln k by dt equal to 1 upon t plus d ln k equilibrium by dt. That means we will get d ln k by dt equal to 1 upon t plus delta U double dagger by RT square. From thermodynamics you got that. So there is two kind of relationship. There is one relationship from here and another relationship from Arrhenius equation. This is equation number 1, this is equation number 2. If you just equate these two equations, you will get 1 upon t plus delta U double dagger by RT square equal to EA divided by RT square. Okay, now so EA will be equal to RT plus delta U double dagger, right? So this is the relationship between the activation energy and the internal energy of activation. Now delta U double dagger will be equal to EA minus RT. Okay, So there is another kind of equation. So now just put the value of delta U double dagger here. Okay, so basically K rate constant equal to KBT divided by H times exponential minus delta U double dagger, which is EA minus RT plus delta N double dagger RT divided by RT times exponential minus plus delta S double dagger by R, which will be equal to KBT divided by H times exponential plus RT minus delta N double dagger RT divided by RT. Okay, then exponential delta S double dagger by R times exponential minus EA by RT. So finally it will be equal to KBT divided by H times exponential RT will get common, so RT will cancel from this expression. It will be equal to 1 minus delta N dagger times exponential minus delta S double dagger by R plus times exponential minus EA by RT. So this is the full expression of the rate constant from transition state theory. Now pre-exponential factor is like this. So this is the Boltzmann factor, exponential minus EA by RT, and this is the pre-exponential factor. So basically pre-exponential factor A will be equal to KBT divided by H times exponential 1 minus delta N double dagger times exponential delta S double dagger times divided by R. Now here look at that, this is bimolecular reaction, right? That means P plus Q to R. So first these two reactant molecules will form an activated complex, let's say PQ double dagger. Then from this activated complex the product molecule will form, right? That means delta N double dagger, which is the number of molecules in the activated complex minus number of reactant molecules. So here PQ double dagger is the activated complex, here this is one complex, so it will be number of molecules in the activated complex is 1 minus number of reactant molecules. Here there is two type of reactant molecules, P and Q, so that's why it is 1 minus 2, which is minus 1, right? So A will be equal to KBT divided by H, then exponential 1 minus 1 minus 1 means it is exponential 2 times exponential delta S divided by R, right? So here the expression the value of A is given, E square you can calculate, KB is given, temperature is given, H is given. Okay, we have to find the delta S double dagger, R is given. So how do you calculate this? So basically exponential delta S double dagger divided by R will be equal to A times H divided by KBT into divided by 1 upon E square, right? So basically delta S double dagger by R will be equal to ln of A times H KBT times 1 upon E square. If you take logarithm of both sides of this equation, so ln means it is E base, remember that. So basically delta S double dagger will be equal to R times ln A H KBT times 1 upon E square. This is the expression of entropy of activation. Now just put the value R. R means universal gas constant. So here the R unit is given, R value is given 8.314 joule mole inverse Kelvin inverse. Okay, so it is 8.314 joule mole inverse Kelvin inverse times ln. Ln means it is E base, then ln A means pre-exponential factor, which is given 10 to the power 13 decimeter cube mole inverse centimeter inverse. Then H, which is the Planck constant, which is given 6.626 times
So
10.
please repeat, sir, from
Okay.
where we are putting the values.
Yeah, I'll just. R is 8.314 joule mole inverse Kelvin inverse, right? Then ln of A means pre-exponential factor. So the value of pre-exponential factor is given, which is 10 to the power 13 decimeter cube mole inverse second inverse. Okay. Then times H is Planck constant, which is given 6.626 times 10 to the power minus 34 joule second. So it should be joule second, right? Then divided by kBt, this kBt, right? kb is Boltzmann constant, which is 1.38 times 10 to the power minus 23 joule Kelvin inverse times T, temperature is 298 Kelvin, right? This whole thing times 1 upon E square. Now E square is unitless. E is, you can put the value in the calculator, the value of E. E square is unitless. So basically what you will get, this whole thing will be unitless. The whole thing inside the ln will be unitless. Look at this. This Kelvin inverse will cancel out each other. This second inverse will cancel out each other. Now at standard condition, means the concentration, the standard concentration is actually 1 mole dm to the power minus cube. So it will cancel, means it will if you divide this, it will cancel. So basically this joule and joule will also cancel. So whole thing inside the ln will be unitless. Okay, so just put all these values in the proper unit, that means in the SI unit here. Now here just the unit of R, which is the joule mole inverse Kelvin inverse, will be the unit of delta S double dagger, right? Is it clear?
Yes, sir. I will solve it. Then we'll tell you what's the value is coming.
Okay. So here just the basic thing is that if you have to just put all these values in the SI unit. So and the good thing is all the values of Planck constant, gas constant, and the Boltzmann constant in this question is given in the SI unit, means in the proper unit. So you have to just put all these values. Okay, you can just solve it and let me know if
So how decimeter cube per mole is cancelled?
So it is actually in the standard condition. The standard condition here, it is in the question is given the C0 is actually 1 mole dm minus cube. So here it is in the actually it is in the standard condition. That means, how do we explain this? Basically what does it mean? It means that the concentration is given in the standard condition, means here, okay, let me just put it here. Total rate of the reaction will be equal to rate constant times P times Q something, right? This is the intuitively for any chemical scheme, the total rate of the reaction, this is rate of the reaction, which will be equal to some rate constant times concentration of the reactant molecules with some order. Now if you just express this concentration value in the standard condition, that means if you just divide this concentration, let's say it is P and let's say it is Q. So if you divide P with P0 and Q with Q0, that means if you divide the concentration of P with the concentration of P at standard condition, or in then it will be unitless, whole thing will be unitless, right? So that is what in this question they are doing. So here rate constant means we are dividing. So here look at the standard concentration is 1 mole dmq, dm to the power minus q. So basically here 1 means we are dividing this concentration with 1. When we are dividing this concentration with the concentration of the respective species at standard condition. So that's why the whole thing will be unitless.
Okay, sir.
Okay. Okay, so just put all these values and let me know what if the answer matches with your expected answer. Okay. So is it clear for all of you, or
yes, sir, clear. I will solve after class, then I will tell
okay,
what's the answer is coming.
okay. So basically in the second question, yeah, I just wanted to tell you, just in the last class, who had joined actually in the last class, so we are discussing that the what should be the rate constant, sorry, the dimension of equilibrium constant, right? Let's say for A plus B to C. Okay, for this reaction, let's say this reaction scheme, the forward rate constant is K1 and the backward rate constant is K minus 1. So the question was, what is the dimension of K equilibrium for this reaction? Okay, now for this type of question, basically in K equilibrium will be equal to the product concentration divided by the reactant concentration, right? Now if you just write it down, the unit concentration, let's say concentration of C is in mole per liter unit, mole liter inverse. Concentration of A is also mole liter inverse unit, and concentration of B is also mole liter inverse unit. So you can get the unit of K equilibrium is 1 upon mole liter inverse, right? 1 mole liter inverse should cancel and 1 will remain. But this should not be true, because we know from thermodynamics that basically any equilibrium constant can be written down as exponential minus delta G divided by RT, delta G0 divided by RT, right? Any equilibrium constant, and delta Z0 is the free energy change. Okay, now we know that the any quantity inside the exponential or ln term so any quantity inside exponential or ln or log term will be unitless, right? So any quantity, whatever it is there or it is there here, so all these quantities will be unitless. So here from thermodynamics we know that the any equilibrium constant can be written down as exponential minus delta Z0 divided by RT. So here this quantity should be unitless and whole quantity should be unitless or dimensionless. So that's why the answer would be the dimension of K equilibrium will be unitless. Okay, just remember that. So how do you justify that? Because when you are expressing K equilibrium in this way, you are getting the 1 upon mole liter inverse, but actually in practical this rate constant will be divided by the value of rate constant at standard condition. Okay, so that's how the whole quantity will be unitless, like it will be expressed like C divided by C0, A divided by A0 times B divided by B0, like this way. So that's why the whole K equilibrium will be unitless or dimensionless. Okay, now major reason is actually for thermodynamics we know that the equilibrium constant can be written down as the exponential of minus free energy change divided by RT. So exponential term is dimensionless or unitless, so that's why the dimension of K equilibrium will be dimensionless. Okay, so there is a small mistake in the last class, so just remember that.
Sir, I have one question. Sir, liter mole inverse was also in option, na?
Yeah.
So what will be the question for liter mole inverse to be true?
No, actually it shouldn't be the true, because actually in practical.
Sir, no, sir. I'm asking that when what will be the question for liter mole inverse?
What would be the question?
For when can we answer liter mole inverse as answer?
So any like 1 upon concentration is liter mole inverse, right? In general, if you just write the concentration in mole liter inverse unit, then 1 upon concentration is actually the liter mole inverse, right? In general, if you write the concentration with the unit mole liter inverse unit, then any 1 upon concentration, which is the inverse of concentration, is actually the liter mole inverse. Okay, actually you should not worry this question, because in the question it is written that what is the dimension of K equilibrium for this type of reaction. Now with this expression, if you write the K equilibrium, you can get this 1 upon mole liter inverse, which is the liter mole inverse. But this is the tricky question, right? So you should not get tempted by this answer, because you know that from thermodynamics K equilibrium is equal to delta G0 exponential minus delta G0 by RT, and this is dimensionless. Exponential quantity is dimensionless, so that's why the K equilibrium is dimensionless. Now what is the justification? Justification behind is that when you write down this type of expression, you just divide this concentration C with the concentration at the standard condition. So by doing this, you can actually get this whole quantity dimensionless. Okay, so that's the justification. Got it?
Okay, sir.
Okay. Okay, so second question is, consider the electrochemical cell which is M solid, then Mi2 solid, then Mi2 aqueous to M solid. So this is the electrochemical cell where M is a metal. Now at 298 Kelvin, the standard reduction potential are given, which is E0 of M2 plus aqueous to M solid is equal to minus 0.12 volt. Okay, and also the standard reduction potential of Mi2 solid to M solid is equal to minus 0.36 volt. Okay, and also there is another quantity is given, which is the delta of E cell, E0 cell divided by del T at constant P, which is 1.5 times 10 to the power minus 4 volt Kelvin inverse. So at this temperature, the standard enthalpy change for the overall reaction is. So we have to find out the standard enthalpy change. Okay, so enthalpy change means delta H. So what we have got here? So basically in the electrochemical cell, let's write it down. M solid, Mi2 solid, this is the anode, and Mi2 aqueous to M solid, this is the cathode, right? So basically cathode reaction is M2 plus aqueous plus 2 electron, then M solid, right? This is the cathode reaction. And let's say E10 is given minus 0.12 volt, and anode reaction is M solid to Mi2 solid plus 2 electron, right? This is the anode reaction. And E20, let's say, is given, which is also the reduction potential, minus 0.36 volt. Okay, so basically the E0 cell will be E0 of cathode minus E0 of anode, right? You know that. So E0 of cathode means E10 here, or E0 anode means, let's see, E20. E10 is minus 0.12 volt, or it will be equal to plus 0.36 volt, right? Okay, so basically (0.24 volt). This is the E0 cell. Okay, now you know that the delta G equal to minus NF E cell, right? You know that the free energy change for any electrochemical reaction will be equal to minus number of electrons that are participating in the electrochemical reaction N. F is the Faraday, which is the 96,500 coulomb mole inverse, and E cell, which is the reduction potential of the cell reduction potential, cell potential. Now for delta G0 case standard condition, it will be equal to minus NF E0 cell, right? So E0 cells you got here 0.24 volt And N, what is the N? N is the number of electrons that are participating in the electrochemical cell reaction. Now let's just consider the cathode reaction here. Cathode reaction is what is happening, M2 plus, which is in aqueous condition. It is ion, positive ion, 2 plus positive ion. So it will just take 2 electrons, then it will reduce to M solid metal solid, right? So what is the number of electrons that are participating? So 2 electrons are participating in the cathode reaction. Similarly, 2 electrons are participating in the anode reaction. So basically N will be equal to 2 here. So delta G0, which is the free energy change, will be equal to minus 2 times 96,500 Coulomb mole inverse times, so Faraday, unit of Faraday is actually Coulomb mole inverse, and E0 cells in 0.24 volt. Now remember that Coulomb times volt equal to joule. Okay, Coulomb times volt equal to joule. So here the Coulomb here, and here it is volt, so it will be joule mole inverse. So minus 2 times 96,500 times 0.24 joule mole inverse. Okay, now what is given? Okay. And also it is given that the delta E0 of delta T constant P, this quantity is given. Now from this equation, if you just take the time derivative, that means delta G0 delta T constant P equal to minus NF, it will be equal to delta E0 delta T constant P, right? Now from thermodynamics you know that this quantity is actually the entropy. Why? You know that the dG equal to minus SdT plus VdP, right? You know that this is the one of the Maxwell equation from thermodynamics. dG, which is the free energy change, equal to minus SdT plus VdP. Now if so, delta G delta T constant P will be equal to minus S. Constant P means this term will be equal to 0, and if you just take derivative with respect to dt, so dt will be equal to 1, and it will be equal to minus S. So delta G delta T constant P equal to minus S. Okay, now just compare this with this. So here delta delta J0 delta T constant P equal to minus S here, so it will be equal to minus delta S0 will be equal to minus NF delta E0 delta T constant P, right? Now so delta S0 will be equal to N minus minus will cancel, NF delta E0 delta T constant P. Okay, so here we got the value of delta Z0. Now here we are doing the value of delta S0, which is the entropy change. So N equal to 2, F equal to 96,500 Coulomb mole inverse times delta E0 delta T, value is given 1.5 times 10 to the power minus 4 volt Kelvin inverse. Now this Coulomb and this volt will together form joule. So it is 2 times 96,500 times 1.5 times 10 to the power minus 4 joule mole inverse Kelvin inverse. Okay, now we have got the value of delta G0 here and delta S0, free energy change and entropy change. Now we know that the delta G0 equal to delta H0 minus T delta S0, right? You know from thermodynamics. We have to find out delta H0 here. So delta H0 will be equal to delta G0 delta G0 plus T delta S0, right? So delta G0 you got here minus, this is this value, minus 2 times 96,500 times 0.24 joule mole inverse. Then T is 298 Kelvin, 298 Kelvin times delta S0, which is this 2 times 96,500 times 1.5 times 10 to the power minus 4 joule mole inverse Kelvin inverse. Okay, now this Kelvin inverse will get cancelled out, so the total unit of delta 80 will be joule mole inverse. Okay, what is the value? If you just take common 2 times 96,500, then it will be equal to minus 2 here from this, minus 2, 0.24 plus 298 times 1.5 times 10 to the power minus 4 joule mole inverse. Okay, so if you solve it, you can get the value of delta 80 in joule mole inverse unit. Okay. Remember that in joule mole inverse unit, whatever is the value is, but here in this question it is asked to compute the delta 80 value, that means enthalpy change in kilojoule mole inverse unit. So basically you know that 1 kilojoule equal to 10 to the power 3 joule. Okay, so let's say here by computing this you have got the value of x joule mole inverse. Okay, so 1 kilojoule is 10 to the power 3 joule, so 10 to the power 3 joule equal to 1 kilojoule. X joule will be equal to x times 10 to the power minus 3 kilojoule, right? This is the conversion factor. So joule, to convert joule to kilojoule, you have to multiply 10 to the power minus 3. Okay, so whatever you have got this value, the delta 80 in joule mole inverse unit, to convert it from joule to kilojoule, you have to just multiply with 10 to the power minus 3. Then you will get the value of delta 80 in kilojoule mole inverse unit. Is it clear? For all the unit conversion and all these things?
Yes, sir.
Okay. Okay, so any other specific doubts from any others? No. So you are so mock thing is continuing or not? So you are
2 tests were postponed this week, na?
Okay.
I think 28 and 29 now.
Okay. Okay, so next week will be the last class, because I've got the notification that 31st January will be the last class. So basically we will cover the electrochemistry and conduction chapter in the next week. And if you guys have any doubts during the mock interview or mock test, you can just post it. So if there are any doubts, I will just log up today, because I'm not feeling okay. Yeah.
Thank you so much, sir.
Yep. So all
Sir,
clear
all
na?
10 to 11 classes were amazing. I have not missed a single one.
Yeah, thank you. Thanks for joining also. So Afrin also all clear? I think, yeah.
Yes, sir. All things are clear. Your classes are too good.
Yeah, thanks for joining.
Thank you so much.
Yeah, bye.